Good.
Okay, let us make a start. So today we're going to basically cover fundamentals of circular functions. So it'll be basically like your basics around degrees and radians, it'll be how you can use the trig ratios, unit circle stuff, and how we evaluate circular functions. So I guess depending on how much attendance we have today, that'll be mainly the agenda, but if it's just going to be us, then I don't see the point where we couldn't do anything else as well. So
Okay.
I'll do this for a little bit. If no one else shows up in a bit, I'll throw it back to you should you wish.
Okay.
But otherwise, yeah. So degrees, radians, and the unit circle. So circular functions introduces this idea of radians. Basically, it's just another way of representing the angles within a circle. So instead of thinking like a circle is completed within 360 degrees, we're now completing it in 2 pi. And the reason why comes from the circumference equation for a circle, that being 2 pi times r. And when you consider that the unit circle is defined as a circle that has a radius of 1, then it follows that the circumference of that unit circle is therefore going to be 2 pi times 1, or just, of course, 2 pi. So in that way, what we have is a way of representing the angles around the unit circle with respect to how much of the circumference has been covered. And so if you ever want to convert between radians and degrees but forget which way it goes, the basic equivalent is that 2 pi is the same thing as 360 degrees. And so all else fails, just start with this and rearrange whichever one you particularly want. In the case of radians, you multiply by pi and divide by 180. I personally think of this as putting pi into the equation. You want to have pi in your answer if it's a radians answer. And then to convert to degrees, you want to multiply by 180 and divide by pi. So again, you want to go to degrees, you want to take pi out of your unit. Then it becomes in terms of degrees. That's at least how I think about it. But otherwise, yeah, just multiplying is really what's happening there. You have like 270 degrees, you want to convert it to radians, multiply it by pi, divide by 180. Trig ratios. So these are all based around specifically right angle triangles. It is worth pointing that out because sometimes you will get triangles that aren't necessarily right angled. And in order to actually use these trig ratios, you're going to have to rewrite your scenario in a way that does contain right angled triangles. And that is possible. It just takes a bit of practice to see how you might achieve that. These can all be memorized from SOHCAHTOA. So the first letter of each of those sections of the acronym is either sine, cos, or tan. And then the remaining 2 letters are just what the ratio is. So if you have OH, that means opposite over hypotenuse. AH, adjacent over hypotenuse. OA, opposite over adjacent. And so basically, if you have any 2 sides of your triangle, you can always calculate the ratio, sine, cos, or tan, depending on which of those sides you have. In this case, you have the hypotenuse and you have the opposite. Reminder that opposite is determined with respect to where the angle is. So since the angle's over here, the opposite side must therefore be opposite it. It's the one that the angle doesn't touch. Angle touches hypotenuse adjacent. This one must therefore be the opposite. And so yeah, that's going to give you sine theta. If the angle was in fact here, you're going to say something?
Oh no, I just turned my mic on because nobody was here. Okay, whatever.
Okay. And if I have the angle here instead, then this 2 would be considered the adjacent, and this would be considered still the hypotenuse. So it all depends really on where theta is.
Okay.
You can also use the exact same thing to figure out the unknown side lengths of a triangle. So in this case, we have a hypotenuse, we have some unknown adjacent side, but we do have an angle. And so again, you still want to consider, even though you technically don't have the adjacent, you at least have a letter that you can work with. And so since we have 2 things for the adjacent and hypotenuse, that tells us that cosine will be useful for solving this one.
Okay.
Yeah. And then from there, simply just rearrange for the unknown. If x is the thing you want, then rearrange for x. In a tech-free environment, this is as far as you can go with that. Obviously, tech-active, you could use your CAS to get like an approximate answer to some number of decimal places. Just make sure that you've got it in degree mode if you have degrees, or radians mode if you have a radian angle. For TI Nspire, that's this button up here. You want to click that until it says radians or degrees, depending on which one you want. Worth pointing out, I think in both of these CASs, there's this thing called gradients. Just leave that alone. Don't use that. I keep forgetting what it is. I do search it up every single time someone asks, but then I forget by the time the next thing comes around. Worth a Google, just in case, but nothing that'll ever be useful for methods. You can kind of do the opposite thing if you have two known sides, but you don't necessarily care about sine, cos, or tan. If you want the angle, what you essentially do is you still start with sine theta equals opposite over hypotenuse, because you have the opposite and you have the hypotenuse. But what you do is once you have that equation, sine theta equals a half, you basically just rewrite it in a way where you wrap the half inside of the sine inverse, and that becomes your theta. Now, if you're good with your exact values, you would actually know what this is. If sine theta equals a half, then, in fact, does anyone want to take a stab at it? If sine equals a half, what must theta therefore be? Cover it in the second document, but I'm curious.
Is it 45 degrees?
Not quite 45 degrees. So a lot of people do think that the half is halfway up the unit circle. It's not quite halfway up the unit circle. That's root 2 on 2. So you got your three values. You got your root 3 on 2, you got your root 2 on 2, and you got your half. So you've chosen, I'm assuming, 45 degrees because you think it's halfway up. With that in mind, what do you think it is now?
Root 2 on 2? I'm not actually quite sure.
That's fine. Yeah, I mean, it's not required right now, but sure, we can do a little quick peek. Sine theta being a half means you got the pi over 6, or the 30-degree one. That's this here, but that's for later. And so sure enough, you're going to get pi over 6 if you're in radians. We typically work in radians a lot of the time. Very rare that you'll actually have a degrees answer when it comes to trig stuff, at least in year 11, 12 anyway. I know earlier years do tend to like playing with degrees a bit. The only time you'll usually get degrees is when you're doing a application style question, and there'll be like, one that comes to mind that happened on an exam was there was like some sort of bridge, and they said, what angle does the bridge make with the floor, or something like that, and it was given in terms of, or it was required in terms of degrees. Other than that, those are some fundamentals basically around trig. Nothing should be too crazy there. You had a question?
So you know how you just showed us that cast like we just like up?
Mhm.
Why is there a restriction on the solve function?
Yep. So that was just me trying to get the exact same answer that sine inverse would give. Whenever you do sine, cos, or tan inverse of a particular thing, it'll give the first angle, or the shallowest angle that would give that particular exact value. Whereas if you do it this way from a solve, there's infinite solutions to this. And so if I don't give it any restriction, it'll grab all the solutions forever.
Oh, okay.
So that wasn't like a question thing. That was more so just like, if you want to use the solve appropriately, you'd want to put a quick restriction on it to make sure.
Like, just a question.
Mhm.
Let's say like so how would you know what restriction to put on it? Would it be specified in the question, or?
Yeah, I mean, look, this will never become an issue. Like you'll be given a domain in the question, and if you're just looking to do, like, if you're just looking to find theta, then you wouldn't even bother with the restriction. You would just go straight into sine inverse of a half.
Yep.
Yeah, like if you just care about grabbing one particular thing from your trig inverse function, then you would just use trig inverse. This is just showing a different way of doing it.
Yep. All good. Thank you.
No worries. And yeah, that's that. Anything else on this document before we move on? And if I go too fast, it'll pop something in the chat. I'm happy to move back. Okay, circular functions with the unit circle. So basically the idea here is you have your unit circle, radius 1, and there's going to be some point that exists along the circumference of that. If you were to draw a straight line connecting that point to the origin, what you can effectively figure out is that there's going to be some vertical component to it, and there's going to be some sort of horizontal component to it. Now, based on our understanding of trig, you can actually grab what those values would be by considering the sine and cosine trig ratios. And the reason why is because in both of these cases, the hypotenuse is going to be 1 because the circle has a radius of 1. And so for that reason, any line that you draw that connects the origin to the circumference has to, by definition, have a length of 1. And so for that reason, if 1 is your denominator, then you basically just simplify down to just opposite and adjacent. Now, worth pointing out, theta is always taken with respect to the origin, and it's in an anti-clockwise direction from the x-axis. So you've got origin, and it's going in that direction. And so for that reason, this is considered the opposite side, and this is considered the adjacent side. So if adjacent is cos, then, well, that's got to be cos. If opposite is sine, well, that's got to be sine. And so what that means for this point is that the total horizontal distance traveled is your x value. The total vertical distance traveled is your y value. Because again, this is centered at the origin. There's no like weirdness going on around there. Clear enough why cosine and sine are the x and y respectively? Whatever mental gymnastics you have to do to memorize that is up to you, but that's kind of like how I always thought about it. Just bring it back down to ratios you already know, and remember that the unit circle has a hypotenuse of 1. Should never forget it from there. Or at least that's my way of memorizing it. This also gives you the result that the gradient of any straight line is going to be tan theta. And the reason why is that tan is specifically defined as the ratio of sine divided by cos. So if you ever divide sine by cos, you always get tan. The reason why that's the gradient is because you're basically doing a rise over run. Your y value is sine, your x value is cos. So when you do y divided by x, you're doing your rise over run. And the reason that works is because your second point is always the origin. So it's like y2 minus 0 over x2 minus 0. Right? So it just sort of simplifies down to just y over x. And so yeah, for that reason, m is always going to be tan theta. So if I like remind you of the that bridge example that I remember, a lot of the time you'll know the angle that your bridge has, and you'll be able to do the tan inverse. Oh, sorry, you'll sorry, say that again. I'm pretty sure you usually get the gradient of your bridge, and you'll be able to do the tan inverse of that gradient to get back to theta. Because of that relationship, gradient is tan theta. Anything to clarify further about that? Okay, next up, quadrant boundaries. These work the exact same way as the xy axis, where everything on the right-hand side has positive x, everything on the left-hand side has negative x. Everything on top is positive y, everything on bottom, negative y. And then obviously there's the individual quadrants that are named. Those are specifically named in an anti-clockwise direction. Because a full cycle around the unit circle is done in 2 pi, it does mean that when you quarter this up, you don't get pi over 4 as the individual cuts, but you get pi over 2 instead. Because 2 pi halves to pi, and then half that again gets to pi over 2. From there, again, because any one of these lengths are going to be a length of 1, it follows that the coordinates at the end of each of these quadrant boundaries are either going to be 0 or 1 respectively, or negative 1, but that's more so just because of where it's located. So if we look at like the total far right, it has no vertical component and it has a fully horizontal component. So the coordinate is therefore 1, 0. So on, so forth for everything in there. Whatever quadrant you end up being in, or at least whatever boundary you end up being in, is the reason why it's going to be either positive or negative. As for tan, since tan is the division of sine over cos, then you simply either memorize your coordinates and do your sine divided by cos, or use a table like this, which is kind of the same thing. The way I personally think of tan is pretty much always exclusively in terms of gradient. So I think this horizontal component, whenever a line is perfectly flat, it has 0 gradient. That's why tan is 0 at those spots. And whenever a line is perfectly vertical, it has an infinite or undefined gradient, which is why tan is undefined at those spots. That's how I personally do my tan values. You can always just do sine divided by cos. That's what I did in school. And then lastly, you'll need to know your interquadrant angles. So we're talking pi over 6, pi over 4, and pi over 3. So 3 more angles that you'll be required to have memorized, and 3 exact values at a minimum that you'll have to have memorized. So we're talking half, root 2 over 2, root 3 over 2. That was mentioned from near the beginning of the lecture. I say these are a minimum to memorize because anything else from there you can create yourself. Like for instance, you don't need to have memorized these tan values, although I do recommend that you do. Technically speaking, you can always do your sine divided by cos to get those values. So at a bare minimum, pi over 6, pi over 4, pi over 3, half, root 2 over 2, root 3 over 2. These are things you unfortunately have to memorize. They will not be given to you on a formula sheet, or at least they should not be given to you on a formula sheet. Otherwise your school is maybe setting up a bit poorly for the actual exam. That's that. And so yeah, basically what we've looked at is how to do the quadrant 1 on a unit circle, or at least mostly. We looked at how to do the angles on the unit circle. We've looked at what the angles are for the unit circle, and we've looked at what the values at those spots are. Now comes actually plotting it out. So angles always go on the inside of the unit circle, and you just write them in ascending order. There's nothing too crazy there. So you start at your horizontal, then you just go from smallest to largest around the entire quadrant. That's nothing too crazy. Pi over 6 is definitely smaller than pi over 4, definitely smaller than pi over 3, definitely smaller than pi over 2. Where it gets a bit trickier is how you arrange these values. This is where I really like thinking about cosine as x and sine as y, because as long as you know root 3 over 2, root 2 over 2, and a half, you can basically just arrange those numbers depending on how large the x coordinate is or how small the y coordinate is, or whichever one you want to focus on. For this, I'll just focus on the x coordinate. If you consider where these angles intersect the x-axis, you can see that as I get a larger angle, I get further up this x-axis. You can see I keep hitting further along this line as the angle gets shallower. And so for that reason, the shallowest angle must therefore get the largest x value. Technically, the largest is down here at the absolute shallowest angle of 0. But if we're just talking purely interquadrant angles, that's why you're going to get root 3 over 2 there. And then all you do from there, well, just arrange them in the ascending order, because as the angle gets steeper, the x value at that spot gets smaller. Once you have one of those, filling out the sign is pretty chill, because literally all you do is you just do the reverse of what you just did. If you did a root 3 over 2, root 2 over 2 and a half, you now do the exact same pattern, but in the opposite direction. So really you just got to pick one of them that you want to outline out, and then the other sort of falls in place. But just for the sake of it, if you care about y values more for some reason, then you can see that as my angle increases over time, I actually get further up the y-axis. So bigger angle means bigger y value, at least as far as this. Obviously these are bigger angles, but We're talking purely for quadrant 1 here. Do I need to explain in any more detail how quadrant 1 works? Has anyone actually got their unit circle memorized pretty well? I'm curious because we've done it a couple of times. I guess it'll really depend on whether or not you're currently looking at circular functions in your school. But okay, so that gets you quadrant 1. The rest of what's going on literally is just going to be reflections. So if you look all around the unit circle, you'll notice that basically all the values are identical, or at least the coordinates are identical, with the only exception being that sometimes they're negative, sometimes they're positive. If you look horizontally or vertically at any given, if we look horizontally or vertically at any given set of coordinates, you'll notice they have the exact same values, but different signs on them. The signs on those values are pure and simple just based on what quadrant it ended up in. In quadrant 1, you have both positive x and positive y. In quadrant 2, you have negative x, positive y. In quadrant 3, you got both negative. And in quadrant 4, you just got the y as negative. That's purely just based on where x and y values are positive and negative. Everything else is literally just copy-paste the value and slap a negative if you need to. That works for any of these. All right, so if you compare the two blues, you can see they're the exact same value, but different signs. That's how we fill out the rest of the unit circle as far as the values go. The last thing to do would be to consider what angles go there. So basically put, every single quadrant has some kind of pi over 6 type angle, some type of pi over 4 type angle, and some type of pi over 3 type angle. They all have exactly one of them. And so that's a little check in your mind to think, have I actually counted around the unit circle properly? Because what I'm going to propose that you do is simply just say, okay, pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6. So you basically just keep counting around the unit circle until you fill everything out that you need. My preferred way of doing this is to think about things in terms of half circles, because that means you've got a nice and easy number to divide with. If it's just pi as a full half circle, then pi over 6 means I want to cut that up into 6 equal parts. Here, 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 here. And then you just duplicate that down here. Pretty chill. What you might have noticed is that pi over 6 does in fact also hit the pi over 3 as well, because 2 pi over 6 is the same thing as pi over 3. It even hits this as well. 3 pi over 6, same thing as pi over 2. So really it just means you need to count this one, and then you need to count your pi over 4s, which again means grab this semicircle, but this time cut it into 4s. That will duplicate a little bit. You'll hit this one again, but that's fine. You'll be able to figure that out. Pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. And then, yeah, you just obviously keep counting around from there. As far as the angles go, I've never seen this come up besides like in a textbook. If you want, you can also just quickly remember that each of those radians angles are related to 30, 45, and 60 degrees. And the same method can be used to count around the unit circle should you wish to really bulletproof this by also memorizing the degree angles. Though I will say, if you're going to, it's hard enough to convince people to memorize the unit circle as is, so if you've got to focus on one thing, do the radians. That is memorizing the unit circle, or at least the sine cos unit circle. Any questions about that? Okay. Now, I did say you need to know your tan values as well, either by calculating them or by having them memorized. I do recommend that you memorize them because it just makes life a lot easier to just notice the value and then immediately be able to solve it. And so to help with that, I've actually created a tan unit circle, which have the 3 exact values that you need root 3 over 3, 1, and root 3. The way you would memorize this one a little bit easier is, well, for starters, you don't have to do anything with the angles. The angles are the exact same as what they are on the sine cos one. But the values themselves, think about in terms of gradient. So steeper angle means steeper gradient. And so for that reason, as the gradient gets steeper, the tan value should get steeper because tan is gradient. So the smallest value goes to the shallowest angle and the biggest value goes to the steepest angle. Technically those should be here and here as the steepest and shallowest, but we're talking interquadrant. As for whether it's positive or negative, well, if you look at these lines, if you imagine them on an xy axis, those are positive gradient linear equations. Same thing here. In fact, for quadrant 3 and quadrant 1, those are just straight lines going up and right. That's a positive gradient. Quadrant 2 and 4, those are straight lines going down and right. So those are negative gradients or negative values. That's pretty much it. Any questions about that?
Chris, so like let's say they give us like tan 30, right?
Yep.
So that would be root 3 on 2.
Tan 30.
Oh, sorry. Root 3 on 3.
Yep, root 3 on 3.
Okay, oh.
Yeah, that's exactly right. Yeah. That'll be covered in more detail in document 3, which is what we'll be doing now. Yeah. So, as you basically alluded to, if you have sine, cos, or tan of a particular angle, then the bare bones basics is just look it up on your unit circle and then give whatever the value is at that spot. In the case of sine or cos, you have to obviously be familiar with the fact that sine is the y value and cos is the x. In the case of tan, well, there's only really one value on that tan unit circle, so nothing too crazy to consider there. So for example, if we're doing sine of 3 pi over 2, first step is just figure out where 3 pi over 2 is on the unit circle, and then because it's sine, you give the y value at that spot, which in this case is -1. If you have an angle larger than 1 revolution, one thing you can simply do is keep counting. So that method of counting that I mentioned earlier, where you just break it up into, well, in this case, pi over 3s. So we had 7 pi over 3. That division of 3 means that you want to count your pi over 3s. Normally you cut off at 6 pi over 3, but if you just keep counting around, you'll hit 7 pi over 3, and you'll realize that that pi over 3 spot is in fact the same thing as the 7 pi over 3 spot. And then from there, everything else just sort of falls accordingly. Right? If you're doing cosine of 7 pi over 3, you're going to give the x value at that spot. So a half. That works fine for small angles, not particularly great for large angles. My recommendation, do a quick division here. Break it into a proper fraction where you've got a whole number and a fractional value. Technically neither of these are whole numbers, but basically whole value of pi, fractional value of pi. And you do that with a simple division. You just say, how many times is 6 going to 55? Well, 9 times with 1 remainder. And then you just put in the pi's there. From there, you look at your whole number. If it is an even number, it means you start on the right. If it is an odd number, it means you start on the left. The reason why. This is an angle of 0. Technically, neither even nor odd. This is an angle of pi, odd. This is an angle of 2 pi, even. 3 pi, odd. 4 pi, even. 5 pi, odd. So on and so forth. All the odds are on this left-hand side, all the evens are on the right-hand side. And so having this big nasty number like this really just breaks down to saying, oh, all I've got to do is start on this left-hand side and then add whatever the remaining angle is. So start all the way on the left. Adding pi over 6 means going forward, so anti-clockwise in a pi over 6 direction. Going anti-clockwise by adding pi over 6. And then you give whatever the value is here. So we cared about cosine, so it's going to be the x value there, -√3/2. Clear enough on how and why that works? And again, if I go too fast, just pop something in the chat. I'll go backwards. Negative angles. So my preferred way of handling negative angles is in two parts. Firstly, if you identify that you have a negative, first thing I would do, knock it off. Pretend it doesn't exist. Just figure out where is the positive version of this angle on my unit circle. And that's this spot here. Next up, remember that you have a negative, and the way to handle it is literally just flip vertically. So if you started here, you would flip up. You always got to flip to the corresponding pi over 6 type angle if it's this one. If it was this one, you would flip to the 3 pi over 4. If it's this one, you would flip to the 2 pi over 3. That's all it boils down to. You're just trying to figure out where am I on the unit circle, and then give my x or y value that corresponds to that. That's pretty much it. Anything to clarify on the lecture so far before we get into questions? Okay, so I'm assuming that doing the actual evaluating of circular functions is probably the harder part of this lecture. So I will bring up the notes or the questions for that. But if anyone wants to do anything specific, then feel free to let me know, and we'll definitely do that. To help out, I will grab some screenshots of the unit circles, although the idea is that you do, in fact, memorize these at some point. So I'll pop those in the chat real quick. Maybe even for fun, we can do a photo of this, just so you know where that came from and which one's cos, which one's sine. Cool. So the way this is arranged in the book is, or at least for question 1, is you're doing both sine and cos at those for these particular angles. So if we do something like, we'll do 1b to start with, first things first is figure out where is 3 pi over 2 on the unit circle, and what are the values at that spot. I'll let you guys have a think about that for now.
Is it just 270 degrees?
270 degrees, I believe so, yeah. Now the question becomes, what are the sine and cos at that spot?
Zero, -1.
Okay, which one's which?
Cos would be 0 and sine would be -1.
Correct. Yeah, exactly right. Cosine always the x, sine is always the y. Nice. A little slightly harder one. So let me see. Let me see if 9 pi over 2 is even a different spot. Yeah, okay. So we'll do part F.
Is it just the same as the last question?
Not the exact same, no. So when you did your counting around, well, I guess I'll ask, did you do the counting method or did you break it into a proper
I
fraction?
So I started at like so since it's like a negative on top, I sort of thought like they start on 3 pi/2, and I thought it's just
Ah,
the same values.
okay. So I did say do F, so I'm assuming you did C.
No, I did F, but if I'm not sure if I did it the right way.
Well, where did you see a negative?
The 9,
There's no negative on that 9 unless maybe there's a bit of a visual bug
no,
there.
like not negative, like odd. Sorry, odd number. I meant odd number. Sorry,
Oh, okay. Yeah,
I'm
odd number.
confusing myself.
Um, so when you do that, you don't look for this as the odd. You look for after you've converted it into a whole number and a fractional number. So you convert your 9 pi/2. Well, I guess I'll just ask, if you to convert your 9 pi/2, what's the whole number and what's the fractional number?
4
Oh,
pi and pi/2.
yeah, it's the whole number that you look at to say whether that's even or odd.
Oh, okay.
So because 4 pi, obviously that's an even, so that means you start
Yeah.
on the right, and then pi/2, well, I'll let you say the rest.
So it'd be 90 degrees, right?
It'd be the 90-degree one, yeah. So sine and cos out those spots now.
Zero and 1.
Which one's which?
So cos is 0 and sine is 1.
Correct. Yeah, precisely. Yeah, that's pretty much it there. So you'll get some more time to practice doing that whole break it down into whole and fractional. We'll do one more just for the just for the hell of it there. 3G. This is more so just to demonstrate the well, how we can pretty easily and quickly figure that one out. Even though it looks like a nasty number.
Just 180 degrees, right?
180. Yeah,
Yes.
correct. So sine and cos are there for
Cos -1 and sine 0.
that's it. Yeah. Sweet. We'll do some tan ones just because why not? Yeah, here you go. Here's some degree stuff. Yeah, why not? Jump straight into 3E so you can have fun with your degrees. For those who aren't super nice with degrees, there is a way to get it back in terms of radians, should you wish to make it more familiar to you.
Is that conversion something like pi over 180?
Yeah, correct. So if you want to convert that to radians, then you want to multiply by pi and divide by 180. Yeah. The way I personally think of it is I'm trying to put pi into my number if it's going to go to radians, so I'm going to multiply it by pi.
It's negative 3 pi, so it would
Mhm.
just be 180 degrees.
Yes. Yeah, the 180-degree spot. That's good. And tan is what at that spot?
Tan is 0.
Tan is 0. Yeah, that's good. Pretty much it for those. These were just the quadrant boundary ones. There are also the interquadrant angles, which we'll now do here. So let's see, what's a fun one? All those just exist on the unit circle. Let's try a few that don't. Let's go with, actually, yeah, let's play a negative, just a simple negative, or at least a simple-ish negative. 3a, sine of negative 2 pi on 3.
Do you flip it vertically?
Well, flipping it vertically is going to be part of it. If you were to explain the full procedure, I could say yes or no to that.
So, so you just flip it vertically.
From where though?
So like right now this is like 270 degrees. So like it's at like the bottom middle. So just go to pi over 2.
Not pi over 2. It's a bit too far. Negative 2 pi over 3 is where we're starting. So step 1 is going to be ignore the negative and just look at where's the positive 2 pi on 3. So if we maybe even just do this one live, we're looking for negative 2 pi over 3. So we're going to start by doing the positive 2 pi over 3, which on the screen share is this spot here. Only now do we then flip this down to the next spot. So flip it vertically. We have a pi over 3 type angle, so you want to hit the other pi over 3 type angle in this spot. And then from there, since it was sine, we're going to give the y value, which is why it's going to be negative root 3 over 2. Okay with that?
Yeah.
Cool. We'll do another negative one. Part F. Cosine negative 3 pi over 4.
Negative root 2 on 2.
Negative root 2 on 2 is correct. Yeah.
Yeah.
That's good. Oddly enough, for cosine, whether it's positive or negative doesn't really matter. Because the x value, whenever you flip vertically, the only thing that changes by flipping vertically is a y value. And so anytime it's cosine plus or minus, that's a little more of an advanced tip for you. Positive or negative on cosine, same thing. But okay, that's that. Next up, I can do another one of those counting around. Let's try a tan. Why not? 3c.
Is it root 3 on 3?
It is root 3 on 3. Yeah, correct. What spot on the unit circle did you get to for that?
So I got so I basically did 2 pi
Yep.
and pi over 6, and it was a positive, so I went to the right and just like 1 up.
Absolutely. So you split that up into 2 pi, which means you start over here, and the remaining pi over 6 got you to this spot. And obviously that would have been on the tan unit circle. That or
Yeah.
you did your division, one way or the other. Yeah, that's that. While I remember, worth pointing out, so on the handwritten bit, I've shown you that these are equivalent ways of expressing the same root. So root 3 on 3 is actually the same thing as 1 over root 3, and root 2 on 2 is the same thing as 1 over root 2. The reason why I highlight this is because some books will use different things, some exams will even use different values. And further than that, when you're doing your actual algebra, it's more likely you get the right-hand side stuff than it is that you get the left-hand side stuff. It just happens to be the case, at least in my personal experience, that if you're doing like actual arithmetic with numbers, you usually get right-hand side looking stuff. So it's worth pointing out these are equivalent. Does anyone need to be shown why these are equivalent? Happy to do a quick demo.
Could you quickly do one?
Yeah, certainly. So this is a technique known as rationalizing the denominator. Does that ring a bell for anyone?
Yeah.
Okay. I'm curious if there's anyone who'd like to take a stab at explaining this one and be brave. Because I know someone here definitely knows it. And it's not just me. No, okay, no worries. So basically the idea is when you have simpler roots to rationalize, it basically means what you want to do is you want to look at whatever the root is in your fraction and multiply a top and bottom of that fraction by that root. Because you can always multiply top and bottom of any fraction by the same number and have it still be a proper fraction. Well, a correct fraction, I should say. The reason why you would do that is because of what ends up simplifying afterwards. So root 3 times root 3, by definition, has to just be 3. And from there, because whenever you do the square root and the square root times each other, you've got to get back to whatever's inside the thing. And then from there, well, you're going to have your 2 on root 3 from there. Wait, hang on. What happened? Why did I do something weird? Oh, have I forgotten this? That's embarrassing. the simplification. Oh, because I did the wrong thing. Root 3 on 2. That's why it was weird. I'll try that again. So it was root 3 on 3. This should have been a 3. And this should have been a 3. And then what you see is top and bottom cancel out, leaving you with 1 over root 3. There we go. Almost screwed that up. Well, technically I did. And then I fixed it. So yeah, that was just me starting with the wrong starting point. So basically, all you do is multiply top and bottom by the root. The two rooted terms will cancel into each other, and then whatever's left on the bottom will usually just fully cancel out. Exact same thing with the root 2 on 2 situation. Multiply top and bottom by root 2, and then those become 2. There's your 2 on root 2, cancel down, 1 on root 2. There we go. Redemption. Did one without stuffing it up. So in that way, you can always convert between one or the other. You can even do the exact same thing from this stage as well. Like if I multiply top and bottom of this by root 3, then again, root 3 and 1 make root 3, root 3 and 3 go back to being 3, which is exactly where we started. So that cycle just repeats over and over. Clear enough? If so, we can move on to, let's say h. H are the hardest one there because you've got to deal with both a negative and a big number. 3h. And it's even a cheeky one too. You'll see why it's a bit cheeky. The voice is gone. Now someone's got to speak up, or at least type out. Have a bit of a bystander effect here. Someone call the cops. No one calls the cops. anyone stuck? Or someone got an idea of what they were working towards so far? Anyone tell me the first step of, or at least my proposed way of handling negative angles? Things first, flip it to positive instead. Just worry about positives to begin with. The next question we have is, how do I convert this positive angle that is larger, clearly larger than 1 revolution? How do I figure out what that is on the unit circle? I'm probably a bit too big to count around the unit circle, so I'd recommend doing a division. Right. Basically, how many times does 3 fit into 21? That'll give you your whole number of pi, and then there'll be some sort of fractional value of pi. Although in this particular case, 3 actually perfectly fits into 21. You get 7. So, oops, let's click with the correct part of the pen. That actually does just simplify it out to 7 pi. Once you have that, you look at the whole value of pi, which is the only thing we have, 7 pi, and we determine if it's even or odd. Evens are all over here, odds are all over here. 7 pi is an odd value, or at least 7 is an odd number, so we're going to start over here. Next, remember that it was negative, so we have to flip vertically. Done. Flipping vertically on the outskirt, it doesn't go anywhere, and so it stays on that spot. So the only thing left to do now is figure out what is the coordinate, or specifically what is the cosine at that spot. You can have 1 participation at the end. Oh, so close. It's on the left-hand side. Fix it quickly. -1. There we go. Left-hand side. So left-hand side always has a negative value over there. And yeah, I mean, that's it. Left-hand side has negative x values. Other than that, that is all pretty much. I'll leave you to it. If there's anything for me to clarify, I'll stick around for a bit. Otherwise, take care.